Dermatoid model, also called a BDT model. For pricing interest rate derivatives, our goal is to construct a binomial tree representing future short rates and use it to price securities accurately. We've implemented this in Python, building on core and the explanations I learned from the John Hall and the online sources. My primary online resources when studying BDT model is from YouTube as well as from GitHub. The core idea of what I did today was to create a code that would represent the model explained in the resource. And this is what we will do for the later presentation. Let's go to the Python code explanation. Let's start with the Python code for our model, the term structure input. This includes the year and the volatilities for bonds with various maturities. Our code prompts users for this data, allowing adjustment as needed. This function collects user input for 5 years of term structures data, and we are going to use table I as an example. I specifically choose this method as it has the flexibility that the professor had mentioned from the class. This is important to be accurate with what's put in. Next, numerical optimization. From line 30, taking initial guesses, for example 10% for year 1, irritative, adjusting the rates until residuals approach 0. Line 31, maintaining precision with XTOL equals 0.001. Line 33, we calculate 0 coupon bond prices using the input yields. Next, we are going to form the tree visualization. Line 35 to 66. Now, let's look at how we visualize our calibrated rate trees. This function takes our calibrated rates and formats them into a readable tree structure. 938 to 42, it calculates the dimension of the tree based on the input. 947, formats each rate as a percentage with 2 decimal places. 953, determines appropriate column width for alignment. Line 62, prints the year numbers as column headers. Line 63, uses a separator line for clarity. Line 65, prints each row of the tree, aligning the rates properly. So the result is a formatted binomial tree that clearly shows how rates evolve over time and across different scenarios. Next is going into our main part of the model for the rate calibration. For the year 1, 1 step, 968. The logic is that first we guess the rates RU and RD, calculate the bond prices at trial nuts, enforce 2 conditions. 973, discounting average price matches year 2's present value. 974, log rate ratio matches input volatilities. 977, the core of a model involves iterative calculation short rates at each nut. We use F-solve for numerical optimization. Next, year 2, 2 steps. 981, the key difference from the 1 step. 997, solve the 3 rates but constrained by RUU equal RUD squared by divided by RDD. This is described in our article. Use the implied years for volatilities. Extends backward induction 1 step further. Next, year 3, and the year 4, 101 to 169. Follow the same pattern with previous year. More nuts, 4 reds for year 3 and 5 reds for year 4. The higher order year calculations and the additional backward induction layers. After we run the Biden core, our model, then we are going to get the result in the right hand side. So you can see we have a table I input, and also we have an output for the binomial tree, the same as our figure F. Now we quickly to summarize our core logic. Here is our key components and the core structures, and calculating zero coupon price. Solving the short race. First, we need to build in the red tree. Next, we are going to focus on our market volatility. This is for our calibration. Then we expanding to the multiple years. There's a total 4 years. We can see we have our very clearly output. So our implementation closely match the original BDT model. However, this is important to note that the model's accuracy can be sensitive to input volatilities, especially in the later years. The use of the numerical optimization also means there might be slightly variations in results depending on the initial guesses and the solver parameters. In conclusion, our Python implementation of the BDT model provides a powerful tool for pricing interest rate derivatives. It allows for flexible inputs, matches market observed term structures, and provides a clear visualization of potential future rates. Thank you.